Welcome to the next lesson on energy changes. This one you're going to need some file paper for, so get a piece of line paper, pause the video if you need to. You're going to put the title, Energy Level Diagrams. Important idea in chemistry. We're going to represent the energy change in a reaction. We're going to use a diagram that tells us about the energy change, tells us if it's exothermic or endothermic. So pause the video while you write that down. So we've said so far that reactions are exothermic or endothermic, and it's all to do with about the bonds breaking and the bonds making. So if you're not sure, go and have a look back, but you have to put some energy in to break the bonds, then energy comes out when new bonds are made, and then the difference between what goes in and what goes out is going to tell us if it's endothermic or exothermic. So as a quick recap, we've said when a chemical reaction occurs, an energy transfer always takes place. I want to write that down as a recap. We said an exothermic reaction, or exothermic reactions, release energy to the surroundings. You release energy to the surroundings, and the surroundings get hotter, if you recall. Or we can have endothermic reactions that take in energy from the surroundings, and the surroundings get cooler. Pause the video if you need to write that down. What we're going to look at is a diagram that's going to show us whether reactions are endothermic or exothermic. We've done a calculation doing the broken minus made in terms of the bonds, hopefully you remember that. Now we're going to look at a diagram. Here we've got A plus B. These are our two reactants. And we're going to make C, and this reaction is exothermic. And we're going to plot a graph of the energy change as this reaction happens. So we're going to have energy on the y-axis, time on the x. I'm going to start with A and B, our reactants. If we don't do anything to A and B, they will keep and maintain this amount of energy forever, in theory, because they won't react. We have to put energy in to make them react. Remember what that's going to do? If we put energy in, what will happen? Well, we said the bonds will break. So we're going to put some energy in to break the bonds. And that amount of energy that we put in that breaks the bonds, we call the activation energy. Hopefully you can read my writing there. It's the activation energy. That's the energy that goes in, that starts the reaction, that breaks the bonds. If we only get to this point, say, here, you can see it, I wouldn't have enough energy to break the bond and the reaction wouldn't start. I've got to get all this energy in. If I don't get to the top up here, I don't put enough energy in to break these bonds, the reaction won't happen. So I've got to put some energy in to break the bonds. But once I've broken those bonds, new bonds are made. If you remember, when new bonds are made, energy is released. So we put some in, and then energy is released. And I end up with my product of C. I put energy in, the activation energy. Then, we've got the energy that's been released. And you can see some went in, but even more came out. And if we look here then, this now becomes our energy change. So we've got to put some energy in, we've broken the bonds, and then even more energy has been released. So what type of reaction is this when more energy has come out than went in? Well, this is going to be an exothermic reaction. So why is it exothermic? Well, we look at our reactants started here. We put some energy in, even more came out. Now we've got our products at a lower energy level. So why is it exothermic? The products have less energy than the reactants. Where has the energy gone? Where has that energy gone? The energy change here. Where has it actually gone, that energy? It's gone to the surroundings. And what will then will probably happen to the surroundings? They'll heat up. We've got an endothermic reaction. Same principle. We're going to have energy and time. And we're starting now with our reactants, X and Y. What are we going to have to do to X and Y to get the reaction started? We're going to have to put energy in. We're going to have to put energy in to break the bonds. What do we call that energy that goes in to break the bonds? We call that the activation energy. Okay? Then, energy is going to come out as new bonds are made, and we're going to form our product Z. What's the difference now? What's the difference now? We put energy in to break the bonds, but not as much energy came out. Not as much energy was given out. So now our energy change now from here shows this is an endothermic reaction. Why is this an endothermic reaction? I think. Look at the products, look at the reactants. Now we can say the products have more energy than the reactants. Where has that energy come from? It's come from the surroundings. We've put energy in, some has come out, but more went in. So overall, more energy has gone in. So now our products have more energy than the reactants. It's a complicated idea. We've talked about the activation energy. You'll need to know the definition of the activation energy. Like I said, it's the energy we put in to get the bonds broken. If we don't put enough energy in, the reaction won't start. So the definition of activation energy is the minimum energy needed to start a reaction. It's a definition that you'll need to learn. So sometimes it might be some reactions might have a high activation energy. Some very low. Some we only need the spark of a match to provide the activation energy to get the reaction started. Sometimes we would need a very high temperature. We talked about sometimes reactions where even the Bunsen burner wouldn't be hot enough. The Bunsen burner wouldn't provide enough energy to get a reaction to start. That means that reaction has a very high activation energy. Some reactions have a very small, some large, but we've got to get to that amount for the reaction to start. Oh, it says it there. I apologise. The minimum energy needed to start a reaction. See, I got it right. I must have been revising. Finally, I'm going to do a quick summary of what we said. We've got our exo, our endo. Do you remember? Exo, it goes up, it comes down further. We've got our reactants and our products. Endo goes up, doesn't come as far. We've got our reactants, products, and if we were going to label what would we say that is? In red, what have I labelled there? You're right, that is the activation energy. Here, in green, would be our energy change. You can remember from the last lesson, if we did the maths to work it out, on the exothermic reaction, do you remember it would be a negative energy value? On an endothermic reaction, it would be a positive energy change value. You'll read more about catalysts later in the next topic. If you want to look at an extension, you might want to see how do catalysts work and how do catalysts affect the rate of reaction. Any questions on this? Check with your teachers. You've got other questions that will be allocated to you now. So try and work out, go through these energy level diagram questions. Thank you.